Good morning everyone. Today we would like to present about the comprehensive analysis of power system protection in terms of challenges, technologies and emerging trends. First of all, we would like to introduce ourselves. My name is Ravinder Lechmanian 2110909881. Next is Mishani Daughter of Kumar 21109098, and then Yogitra Ganesan 21109091. And the last one is Karthik Anarathi Murthy 21109092.
Power system is composed of the components or elements such as generators, transformers, transmission line and distribution lines, bars and others. Short circuits and other abnormal conditions in the power systems are common and can cause damage to power system equipment. The equipment in the power system is protected by the protection of components, which include relay, circuit breaker and other components. Power system protection serves the primary function of shielding all system elements and components such as transformer, generator, transmission and distribution lines, bus bar and other from potential harm like short circuits and other irregularities that frequently arise in the power system. To save life and prevent fire from spreading to buildings and other property from fire, protect electrical equipment damage and fire. We obtain 5 objectives in the power system protection, and the first objective is the power system stable. By isolating only the malfunction components and keeping the majority of the network up and running. Besides that, the second objective is protection system need to be able to recognize abnormal or fault condition fast in order to isolate the affected portion, and the third objective to maintain system functionality for the remainder of the power supplies and reduce the possibility of damaging other equipment. Reducing the number of equipment disconnection is necessary to isolate the malfunction from the systems. Then fourth objective is the protection need to be steady enough not to activate when the connected equipment is carrying the maximum rated current, which might be yet sensitive enough to activate when a fault arises under mild function condition but sufficiently steady to avoid functioning when the connected equipment is using the maximum rated current, which might be a temporary value. Last objective, operate reliable and quickly enough to remove the fault from the system with the least amount of damage to its constituent parts. Next is how the fault is happening. A fault in a power system is a defect that diverts current from the intended path, reducing insulation strength between conductors and causing excessive system damage. Electrical faults occur when voltages and current deviate from nominal values, causing damage to equipment. Fault detection and analysis are crucial for designing suitable protection device and switchgear. Fault in the power system caused by insulation failure, flashover, physical damage, or human mistakes. First type of fault is open circuit fault. One or two wires failing is the main cause of the open circuit fault. The term series fault refers to the open circuit fault that develops in series with the transmission line. The open circuit fault classified as open conductor fault, 2 conductor open fault, 3 conductor open fault. The next is causes and effect of open circuit. Caused by a faulty circuit or broken conductor in a single or several phase. The consequences of the open circuit are the electrical power grid operates irregularly. Faults can be a hazard to both animals and humans when the voltage is raised over typical levels in some parts of the network. Insulation fails and short circuit issues emerge, and even though this kind of circuit faults may be tolerated for a longer period of time, then short circuit fault must be disconnected in order to reduce the severe damages. And the next fault is short circuit fault. Short circuit fault are brought on by breakdowns in the insulations that separate phase conductor from ground. A short circuit path may be created by a failure of insulation, which will result in the internal short circuit circumstances and anomalous connection with the extremely low impedance between 2 points of varying potential. Whether intentional or accident, it's called a short circuit. Short circuit faults can be classified as symmetrical fault and unsymmetrical fault. And causes and effect of short circuit fault. Causes of a short circuit fault can be a fault may emerge due to internal or external influences. Internal impacts include transmission lines failure, equipment damage, insulation aging, insulation corrosion within the generators, incorrect installation of the electrical device and transformers, and inappropriate designs and fault can arise a result of outside effect of the equipment. Insulation failure due to the illumination surges or mechanical damage caused by the public. The consequences of the fault can be arcing faults may lead to fires and explosion in equipment like as transformer and circuit breakers, and if the short circuit mistake persists, the flow of electricity may be significantly reduced or completely damaged. As presented before, short circuit fault can be classified as symmetrical fault and unsymmetrical fault, and the first one is symmetrical fault. Fault which give rise to symmetrical fault current is called a symmetrical fault. Equal fault current with under 20-degree displacement. The phase lines are simultaneously short circuit or three-phase to ground fault is an example of the symmetrical fault. Only one phase is considered for calculation. Condition for remaining two phases are remain same. The symmetrical fault is rarely occur and most severe. The symmetrical fault is subcategorized into line to line to line fault and three-phase line to ground fault. And the last part is unsymmetrical fault. Fault which give rise to unsymmetrical fault current is called unsymmetrical fault. Magnitude of a fault current are different with equal phase displacement. Unsymmetrical fault are single line to ground fault, line to line fault, and double line to ground fault. Majority of the fault on the power system are unsymmetrical in nature.
Now let's explore the components of power system protection. Relay function as the sensory devices in power system, often referred to as brains due to the decision-making capabilities in fault detection. They work by measuring the voltage and current, converting this into digital or analog signal, and then isolating the malfunctioning circuit to prevent damage. Modern relays are advanced, featuring communication capabilities for remote control, diagnostics, and monitoring. They can capture the fault event, providing the critical data for the post-fault analysis, thus enhancing the overall protection and management of the power system. Next is circuit breakers. Circuit breakers are electrically operated switches designed to open and close circuits safely. They receive the input from the relays and use the tension closure spring to keep the contact closed when in the closed position. Upon detecting a fault, the trip close releases the latch, quickly opening the circuit to isolate the fault. Circuit breakers are essential for maintenance and repair, allowing a safe isolation of the system segment. Modern circuit breakers often include the remote control and monitoring features, improving the management efficiency and response time. The overcurrent protection scheme is vital for detecting and responding to excessive current flows which could result from overloads or short circuit. By monitoring the current level and isolating the section of the network experiencing overcurrent condition, this scheme prevents the overheating and equipment damage, prolonging the lifespan of the critical component like transformers and generators. It ensures only the affected parts are isolated, minimizing the disruption to the overall power supply. Differential protection scheme. This scheme works on the principle that the current entering the protected area should equal current leaving it. Any discrepancy indicate the fault within the section. The differential protection is highly effective for equipment where both ends are closed, such as transformers. It ensures only the internal fault, trigger the isolation, maintaining the system stability by distinguishing between the internal and the external fault. However, it is less suitable for the long transmission line due to the physical distance between the endpoints. Distance protection scheme relates the voltage and the current at the same end to calculate the impedance, which help locate the fault. By comparing the impedance to the preset value, it determines whether the fault exists and its distance from the protection site. This system is particularly useful for the transmission line as the impedance is proportional to the distance of the fault, allowing the precise fault location and quick isolation of the faulty sections. Directional protection scheme determines the direction of the fault current flow to accurately locate and isolate the fault. By identifying whether the fault current is moving towards or away from the relay, this scheme ensures only the affected segment is isolated, preventing the unnecessary power disruption. This is especially important in complex systems with multiple power flow, maintaining the stability and the reliability by working with the protective device to efficiently isolate the fault. Furthermore, each component also plays an important role in power system protection by ensuring the reliability and stability. First of all, let's see about the relay in ensuring the reliability. Relay are crucial for the reliability of the power system due to their ability to quickly detect and isolate the fault. By continuously monitoring the electrical parameters such as voltage and current, relays can identify the anomalies indicative of fault. When a fault is detected, relay trigger the protection device like a circuit breaker to disconnect the malfunctioning section, prevent further disturbance and minimizing the outage duration. In addition to the fault protection, relays plays a vital role in maintaining the power system stability. They monitor the critical parameters such as frequency and voltage, responding to the deviation by activating the compensatory mechanism like a voltage regulator. For instance, if a sudden increase in the demand causes a voltage drop, relays can initiate the corrective action to restore the voltage level. Circuit breakers are essential for the power system reliability as they provide the prompt protection against the electrical fault. When a fault is detected, circuit breakers quickly isolate the affected section, protecting the vital components such as transformers and generators. This rapid isolation reduces the impact of fault on the overall power supply, ensuring that the unaffected areas remain operational. Circuit breakers enhance the power system stability by swiftly isolating the fault, preventing them from causing a broader network disruption. This rapid fault containment helps avoid a large scale of outages and the potential cascading failures. Modern circuit breakers with the features like this, remote control and monitoring, allow for the efficient administration and quickly restoration of the services. Protection schemes are internal to the power system reliability as they detect and isolate the fault rapidly. By continuously monitoring the electrical grid of the irregularities such as short circuit or ground fault, these scheme active relays or circuit breakers to disconnect the affected area. Protection schemes are pivotal in maintaining the stability of the protection system. By quickly isolating the fault, this scheme prevent the disturbance from spreading and causing widespread outages. Coordinate action within the scheme ensure the selective deactivation of the specific area, minimizing the overall impact of the fault and enhancing the system resilience. Efficient fault management by protecting the scheme preserve the balance and stability of the power network, ensuring the consistent electric flow. We are also facing some challenges in power system protection. The first challenge is blinding of protection. Blinding of protection occurs when the relays or system fail to detect or respond to the fault due to the factors like load, enroachment or high resistance fault. This reduced sensitivity can lead to the delay or missed tripping action, increasing the risk of equipment damage and stability issues. Modern protection systems often use adaptive relaying and advanced fault detection algorithm to maintain the effectiveness under the varying condition, mitigating the risk associated within the building. Next challenge is false tripping. False tripping involves the protective device mistakenly disconnecting circuit without fault, caused by the incorrect setting, electrical noise, or equipment malfunction. This result in unnecessary power outages, reduce the system reliability, and increase the maintenance cost. To minimize the false tripping, advanced algorithm, precise setting, regular maintenance, and modern digital relay with the improved filtering and signal processing are essential to ensuring the accurate fault detection and system stability. The last challenge is recloser fuse coordination problem. Recloser fuse coordination is the critical for maintaining the grid reliability. Recloser attempt to restore the power after temporary fault, while fuses provide the backup protection by isolating the fault section if the recloser fails. Proper coordination ensures the recloser operates first, allowing the fault to self-clear with the fusing acting if fault persists. Optimal coordination involves in setting appropriate time current characteristics, considering the fault current level and the system topology, enhancing the grid reliability and minimizing the disruption. I would like to show a real-world case study which is microgrid protection. In microgrid, the integration of distributed energy resources, which is DER, present unique challenges. Blinding of protection occurs when the DER reduces the fault current, delaying the fault detection. False or sympathetic tripping happens when the DER contributes the fault current, causing the relays to misoperate and isolate the unaffected feeders. Recloser fuse coordination ensures the reclosers operate before the fuse for the temporary fault, maintaining the system stability. Addressing these issues is essential for the effective microgrid protection and reliability.
Model technology in power system protection. First is numerical relay, an advanced protection device that leverages microprocessor based technology to offer programmable and customizable protection characteristics. This relay provides a comprehensive suite of functions, including overcurrent, distance, difficulty, and earth flood protection, as well as a real-time measurement and monitoring. This supports various communication protocols such as IC 861850, DNP3, and Modbus facility integration with other systems. Second one is digital signal processing, DSP. playing a critical role in power system protection by providing the precious and reliability of protection relay. DSP technology limited noise and process signal accurately, enabling real-time analysis of electrical parameter and the implementation of diesel protection algorithm. This ensures swift and accurate fault detection and response, contributing to overall system reliability. Third one is communication system are effective for effective power system protection as they enable seamless information exchange. These systems support remote monitoring and control, allowing operators to manage the system centralized. They also facilitate fault detection, classification, locating, and integration with the SADA system to enhance system efficiency and reliability. Advantages and limitations of numerical relay. Numerical relay offer features advantages in power system protection. They provide features fault detection, which is reduce unnecessary trip and ensuring system reliability. The adaptability and programmability allow for tailored protection setting and algorithm. The communication capability of numerical relay enable seamless integration and remote monitoring or control, while the data recording and analysis features provide ensuring event data for improving system maintenance. However, numerical relay also have a limitation. Their complexity requires skills personnel for setup and maintenance. They involve a high initial investment compared to older technology. Potential software glitches and cyber security risks can affect the reliability, and integration relay from the different manufacturers can cause compromise. Advantages and disadvantages of DSP. Digital signal processing DSP technology offers several advantages in power system protection. It is ensure high precision in fault detection, resulting in accurate if protective action and reduced fault stripping. DSP systems are enterable and programmable, allowing for the customized protection settings and algorithm. They provide real-time processing capability, ensuring the accurate fault reason. DSP technology also facilitates data analysis, expecting key features for the fault detection and classification and improve overall system effective throughout integration with the model system. DSP system also limitation. Their complexity make them challenging to configure and maintain. The initial cost of implementing DSP technology is higher compared to the traditional method. Reliability cons such as potential software bank and cyber security trend can impact system stability. In addition, integration different DSP system can be difficult and a stable power supply is necessary for the effective operation. Advantages and limitations of communication system. Communication system enable coordinated protection strategy, ensuring swift response to the fault. Remote monitoring and control capability allow for the centralized management of the system coordination, ensuring operation efficiency. Real-time event reporting improves system reliability and control, and cybersecurity measure protected data and control command for the nation trend. However, communication will also present challenges require skilled personnel for setup and maintenance. The initial investment for this system is higher compared to the traditional method. Reliability cons such as communication fail and cyber security risk can affect the system stability. Emerging trends in power system protection. Emerging trends including the integration of artificial intelligence AI and blockchain technology. AI technology such as artificial neural network (ANN) and Wattlet transformer enhance plot detection by learning for the historical data and analysis high frequency component. Using logic control FLC and adapting neutron fusion influence system ANFIS provided adapting and pressure control, improving overall system reliability. Blockchain technology offers secure and transparent transaction recording throughout the emulating lag. The decentralizing nature of the blockchain increase system reliability and reduce the risk of cyber attack. Additionally, the smart contract automate version process from fault response to maintenance, achieving the effectivity and reliability. Additionally, smart contract automate version process from fault response to maintenance, ensuring efficiency and reliability. Benefit and challenges of AI integration. The integration of artificial intelligence AI in power system protection offers several benefits. AI ensuring accuracy by the providing precious fault classification and promote response. It enables real-time monitoring, allowing for the easy fault detection and proactive maintenance. Automation throughout AI operation system operation and result in cost saving. AI also allowed for the seamless integration with the IoT, SCADA, and advanced monitoring system, enhancing overall system functionality. However, implementing AI in power system protection presents challenges. The complicated of the AI system required specifically expanding and resources. Protection sensitive power system data by cyber threat is crucial. Accessibility issues may rise the managing largest volume of data in real time, ensuring interoperability between difficult AI systems in ensuring the soft operation. Benefit and challenges of blockchain integration. Blockchain technology integration offers immutable record keeping, ensuring secure and transparent transaction recording. The decentralized nature of block diagram enhances durability and reduces the risk of cyber attacks. Smart contract automate process and streamline operation improve efficiency. Blockchain also ensure data access throughout the carry photography linking of the block. However, blockchain integration presents challenge. Collaborating remain an issue in handling largest value of transaction in real time. The energy consumption associated with the proof of work (POW) assume mechanism reach environmental cost. Navigating regulating completion and data private law is essential for the blockchain implementation. The complexity of integration blockchain into the existing system requires scientific effect and investment. Additionally, the cost of developing and maintaining blockchain network can be high.
In 2012, India was severely affected by the largest power outage in history. On 30th of July 2012, on the northern grid, the circuit breaker of 400 kV line tripped. This line fed into another transmission line. The circuit breaker of this line tripped and failure cascaded along the grid. On 31st of July 2012, on eastern and northeastern grids, the line tripped again due to a relay problem and resulted in cascading failure at the grid. The cause was overdrawing of power that caused significant strain on the grid. Consequently, the grid was experiencing a crucial frequency fluctuation due to the imbalanced supply and demand. This resulted in the tripping of multiple lines and power stations. In 2013, Wide Area Monitoring System installation was initiated in India. WAMS is an advanced sensing and measurement system. This system continuously measures and monitors the power grid. WAMS prevents system overloads, instabilities, and cascade tripping that can lead to power blackouts. WAMS consists of phasor measurement unit and phasor data concentrator. The function of PMU is to monitor load and temperature on the power lines and determine the magnitude and phasor angle of the sine waves at different locations. PDCs perform real-time monitoring, alarming, and triggering. In 2015, severe grid disturbance occurred due to the factors such as high demand and generation shortfall. Significant frequency fluctuation and voltage instability was detected. WAMS provided real-time monitoring of electrical parameters. The PMUs provided time-synchronized data on voltage, current, and frequency. The system detected unusual power flow patterns and significant frequency fluctuation in real time. The potential risk zones were identified in the grid. These zones were declared as the high risk and unsafe zones. The WAMS triggered automated alerts to the grid operators. The severity of the situation was indicated. Grid operators identified the critical zones that need to be attended based on the signal provided by WAMS. The system recommended immediate load shedding in non-critical areas to reduce stress on the grid. Grid operators adjusted power flows and reconfigured the network to stabilize the voltage frequency levels. The faulty transmission lines and affected areas were isolated to prevent the fault from spreading. The fast act of isolating the faults helped in maintaining the functionality of the rest of the grid. The outcome from the installation of WAMS is the northern grid remained stable, the potential blackout of the nation was prevented, and the power supply was maintained at critical infrastructure areas. This minimized the impact on the population and economy of the country. The case study discussed provides an insight on the effectiveness and importance of implementing power system protection measures. The lesson learned from this case study is implementation of power system protection measures WAMS provides an enhanced grid stability. The continuous monitoring and real-time data allows immediate corrective actions to maintain the stability of the grid. Consequently, the early detection and isolation of faults prevents the initial problem from escalating into blackouts. The automated alerts and detailed awareness provides enables and grid operators to respond and act fast effectively. The system's recommendation optimizes the performance of the grid during interference. As a conclusion, the power system protection is essential for ensuring the reliability and safety of electrical power systems. By swiftly detecting and isolating faults, equipment damages can be prevented, power outages can be minimized, and the stability of the entire network can be maintained. Advanced protective relays and automated systems enhance fault detection and response time, improving the overall efficiency. The potential future development in power system protection are most likely to be influenced by technology advancement, shift in energy landscape, and the importance of reliability and resilience. The potential future development in the power system protection is the smart grid with self-healing ability, where the grids will be able to automatically detect, isolate fault, and reroute power to minimize power outages. Next, IoT offers real-time monitoring and control capabilities, significantly enhancing situational awareness and enabling quicker fault detection and isolation. The incorporation of artificial intelligence and machine learning in the power system protection through predictive maintenance and enhanced fault detection. A more sophisticated relay and adaptive protective scheme can be developed in the future. Continuous advancement in technology and smart grid integration are further refining protective schemes, making power systems more resilient. Effective power system protection is crucial for maintaining consistent and secure electricity supply to consumers.